Okay, here we are going to take our velocity level equations 1 and 2, put them into matrix form in the sense that it's going ax equals b, and we're going to solve for x, in which in here x is going to contain the rate of change of our unknowns, which are theta 1 dot, theta 3 dot, d4 dot, d5 dot, right? So if you recall, we assume that we have performed the position level analysis when we go about doing velocity level analysis. Thankfully, indeed, we have done that in the first video. So we know theta 1, theta 2, theta 3, d4, and d5. Moreover, what is also given to us is theta 1 dot, which is the link that we are driving. So we have a motor attached to that link, and we know what the rate of change of that link is. So those are our knowns. So what I want is an equation of this form: a times x equals b, where x is going to contain my unknowns. What are my unknowns? Well, they are theta 1 dot, as I said, theta 2 dot, well, not theta 2, sorry, theta 3 dot, d4 dot, and d5 dot transpose. In other words, the unknown vector x is going to be 4 by 1. Sorry, let me try to write this a little bit neater. It's going to be a 4 by 1 vector. The known vector b is going to be also a 4 by 1 vector, because we have 4 equations, right? We have the first 2 rows of this equation, they are non-trivial. They give me 2 equations, and these equations, the first 2 rows of the velocity level 2 set of equations, give me 2 other scalar equations. So in total, I have 4 scalar equations. So the vector b is going to contain 4 elements, so it's going to be a 4 by 1 vector as well. So we write that by saying b is an element of R4. So A is a matrix that takes a 4 by 1 vector and gives me another 4 by 1 vector, which means that A must be a 4 by 4 matrix. Okay, let's populate this matrix A. Okay, so since my unknown vector is going to be theta 1 dot, theta 3 dot, d4 dot, and d5 dot, what I can do is I can go back to my first equation here, observe what multiplies theta 1 dot, and write it as the first element in the first row of the matrix A. So if you look at here, again, I'm over here right there at the top of the page. My eyes are looking at that row, and I read off the coefficient of theta 1 dot in that equation. And what I see there is minus d4 times cosine of theta 1. Again, in the same equation, I'm looking at the same equation, and I'm looking at what multiplies theta 3 dot in this case. And I see no coefficient that does that. In other words, the coefficient is 0. So I can go ahead and write here 0 as the coefficient that multiplies theta 3 dot. So look at this. This is the second element in this vector. This is going to be the second element in the first row of that matrix. Okay. Okay. So again, I'm looking at the same equation, and I'm looking at what multiplies d4 dot in this case. And I see that that is equal to negative sine of theta 1. And then again, I'm looking at the same equation, looking to see if I see a d5 dot, and I fail to see one. So the coefficient of d5 dot in that equation is 0. Very good. Now I'm looking at the second equation here, or this second row of this equation VL1, and I am going to identify what multiplies theta 1 dot again. And what I see is that is negative d4 sine of theta 1. Again, in that equation, I'm looking at what multiplies theta 3 dot. I see nothing, so another 0 comes in here. I'm looking at that equation, looking at what multiplies d4 dot. I see a cosine of theta 1. And what multiplies d5 dot is again 0. Okay, those are the first two equations. Now, let me look at this equation here, the first row of that equation. I'm going to identify what multiplies theta 1 dot. I see a minus a1 cosine 1. What multiplies theta 3 dot in the same equation? I see a a3 sine theta 3. What multiplies d4 dot? I see as nothing, so it's a 0. What multiplies d5 dot? That's a 1. In the second row of VL2, looking at those equations now, what multiplies theta 1 dot is minus a1 s1, or sine 1, theta 1. What multiplies theta 3 dot is minus a3 cosine of theta 3. What multiplies d4 dot and d5 dot, they're both 0. So a 0 here and a 0 there. Okay, what is my unknown vector, or sorry, what's my known vector here? Yes. Actually, that's fine. Okay, I need to go back to my first equation right there. The knowns are collected in here, you can see, because I know everything in this here over there. I know everything about it. I've already taken care of these parts of this equation. They are lying in the matrix times vector product right there. Okay, so the only vector that is unaccounted for is this. So now I'm taking those knowns to the right hand side and writing them down over here. Okay, so if I take that first row to the right hand side, and what I get is a negative a2 cosine theta 2 dot. Okay, now I'm looking at the second row here, and I'm putting it on the right hand side, and then a negative is going to appear. That's going to be a negative a2 sine theta 2 dot. Coming down over here, looking at the first equation, what is the known vector? Well, I've accounted for all of these things actually. All of them are accounted for. The known, there is no known, so these are all zeros. Okay. So let me simplify this equation. What I can do is, instead of writing it this way, I can write a2 theta 2 dot here, and then this vector is going to be, actually I can even put the minus over there, cosine theta 2 sine theta 2 0 and 0, and I can get rid of this. All right, very good. So we have constructed our A matrix and our known B vector and our unknown X vector. Now all there is left for us to do is plug in the whatever is known about this matrix. Everything is known about that matrix. Just get a numerical value, and get a numerical value for the right hand side, and then solve that linear system of equations. And in the next video, I'm going to talk about the acceleration level analysis. But before I start doing that, I'm going to use MATLAB or whatever. I'm going to use actually Julia in the background and solve these equations, come up with the values of theta 1 dot, theta 3 dot, d4 dot, and d5 dot, and then use those values in the acceleration level analysis. All right, I'll see you later in the acceleration level analysis video.